Good morning. Welcome to this Conservation Applied Research and Development webinar, which reports on overcoming the market barriers for rooftop unit or RTU retrofit enhancement. Thank you so much for joining us today. I'd like to cover a few housekeeping items before we start. All attendees will be in listen-only mode. We will answer all questions at the end of the presentation, but as questions occur to you, please type them into the Q&A box and send them to all panelists. The Q&A box can be opened by clicking the ellipsis in the lower right of your screen as indicated on this slide. We will do our best to answer all questions within the time allocated, but if we don't get to some, we will answer them after the webinar. This webinar is being recorded and will be available on the department's website in a few weeks. The slide set from this webinar will also be available on the website, but if you need it sooner, email me directly. And finally, if you'd like the closed captions on this webinar, click the CC bubble on the lower left of your screen. I am Lindsay Anderson. I'm an analyst and research planner at the Minnesota Department of Commerce Division of Energy Resources. In this role, I identify and analyze gaps within utility conservation improvement programs and coordinate and plan research to fill those gaps. The CARD program is a major tool of that work. I'm also the department's project manager on the research that is the subject of this webinar and will be moderating the Q&A portion of today's presentation. Our presenters today are Alex Haynor and Mason Miller from Center for Energy and the Environment. Alex Haynor is a research engineer at Center for Energy and Environment, where he has worked since 2010. He conducts research on emerging technologies in residential and commercial HVAC systems with a focus on field instrumentation and data analysis. Next, we have Mason Miller, whom is a research analyst at Center for Energy and Environment, where he deploys data monitoring equipment and provides data analysis for CEE's various energy efficiency research projects. Welcome to both of you, and we look forward to the presentation. This webinar is one in an ongoing series designed to summarize the results from research projects funded by Minnesota's Applied Research and Development Fund, which was established in the Next Generation Energy Act of 2007. The purpose of the fund is to help Minnesota utilities achieve their energy savings goal. $2.6 million is set aside annually for the CARD program, which awards research grants in a competitive request for proposal process. Results from CARD projects provide utilities with data to enhance energy efficiency program designs within their conservation improvement program portfolios. As you can see by the pie chart, CARD projects funded to date have been in all building sectors, as well as some that cross multiple sectors. The subject of today's webinar is within the commercial sector. This recent CARD project analyzed the market barriers for RTU retrofit technologies, field-tested energy efficiency improvements for existing RTUs, and then developed strategies to overcome the market barriers to proven energy efficiency improvements of existing rooftop units. Now I'll turn it over to Alex for today's presentation.
Great, thank you, Lindsay. Hello, everyone. My name is Alex Haynor. I am a research engineer at Center for Energy and Environment. I am joined by my colleague Mason Miller, and as Lindsay mentioned, we will be talking about a CARD-funded research project we conducted titled Overcoming the Market Barriers for RTU Retrofit Enhancements. Before we kind of jump into the project here, I just wanted to start with some background on CEE and what we do. So we deal with all things related to energy efficiency. This includes programs such as Home Energy Squad and one-stop commercial lighting programs, recommissioning and consulting work. We also do financing and policy work. The group that I'm involved with is the research group, and we conduct research projects in many areas, including HVAC, program design, indoor air quality, but we focus on field applications and market studies of energy technologies and ideas, and we will be touching on one of those projects today. So CEE has been involved in multiple research projects related to rooftop units over the years. The first project was a CARD-funded study in 2013 and involved field testing of a variety of retrofit packages that were kind of in the early phases of their development. So two of the packages that were studied as part of that project will be discussed in this presentation. The second CARD project was a characterization study to perform market research to determine various characteristics about the RTU market in Minnesota. So these projects really taught us that the RTU market is large and retrofit packages can offer tremendous potential. So the characterization project found that 80% of commercial buildings in Minnesota are served by RTUs. This is around 21,000 buildings. Extrapolating from that characterization study tells us that there are around 154,000 RTUs serving Minnesota buildings. And kind of in that research, we found that the majority of these systems are standard efficiency and could absolutely benefit from an efficiency upgrade. Now, before just jumping into the project, it's important to define what an RTU actually is and then what our focus was for this project. So there are many HVAC systems that reside on a rooftop, such as a dedicated outdoor air system, condensing units, heat pumps, VRF systems, cooling towers, etc. But the systems that we focused on with this project are packaged RTUs. So a packaged RTU combines heating and cooling systems into a single package to condition a building. In Minnesota, we find that they are mostly gas-fired heating and direct expansion cooling systems, but some do combine with boilers or electric resistance to provide space heating. So an RTU differs from a residential system in a few ways. First of all, it is condensed into a single package, kind of shown here in this diagram. But the main difference is really how it routes air through the system. So a key component of a packaged RTU is the damper system that opens and closes to route air, return air, and outside air throughout the unit. So an outside air damper, which we call an economizer, you can see in kind of the upper right-hand side of that diagram. So this is used to allow fresh air to enter the RTU. And this air can either receive conditioning during heating or cooling events, or be brought in simply as fresh air to provide ventilation to the space. So in addition to providing fresh air for ventilation, economizers have the ability to cool a space if the outside conditions are favorable. This we call free cooling. So RTUs can also use a variety of controls, but they often rely on standard thermostats. So building automation systems are also common. Usually these are found on larger systems or buildings, but ultimately it depends on the building type and then how the customer wants to control the system. So the project contained 5 overall tasks. First, we conducted a technology assessment. So this was a broad scan of the RTU retrofit market to determine available RTU retrofit technologies. And this is both updated packages from previous research as well as new products on the market. Next, interviews with key industry professionals and utility representatives, really to determine the current state of the market and then any perceived barriers to implementation of these systems. Field measurements were conducted across 8 field sites and 5 different retrofit technologies. Energy savings calculations were done to predict annual savings for each package and then finally results and recommendations for RTU retrofit kind of energy and cost savings, and then recommendations for just the overall retrofit potential in Minnesota. So starting with the first task of the project, which was the technology assessment, key information was gained about the available RTU retrofit packages from research and manufacturer interviews. Our goal here was to determine the packages that could most benefit Minnesota RTUs. So the goal of the assessment was to find specifics such as ideal application, including RTU size, configuration, space type, current manufacturers of these technologies and packages, the prevalence in the current market, control strategies that were employed, and then ease of installation, installed cost, and overall energy savings potential. So there are a variety of technologies available that can offer energy savings on a packaged RTU, which is shown here in this diagram. First, we have evaporator fan control. This is one of the most common, and this decreases the speed of the fan providing air to the space. Typically, this is called a supply fan. Advanced economizer controls offer more robust controls for determining when to open the outside air damper. Demand control ventilation, commonly known as DCV, uses a CO2 sensor in the conditioned space. Typically, this is in the return air to determine when CO2 levels are high and ventilation is necessary. Zone control is for larger RTUs that serve multiple space types and only sends conditioned air to the required area. Fault detection and diagnostics, this places sensors on various components of the RTU. This is done to identify faults and then alert facility managers of those faults. Advanced thermostats allow for RTU coordination and scheduling. And then finally, compressor control varies the capacity of the system during cooling events. So as you can see, there are many different ways to increase efficiency on an RTU. So this table, which I understand is hard to read, really just shows a summary of the retrofits found through the assessment. Now, this does not include every available package or technology, but really what we consider the most relevant to Minnesota RTUs and gives an idea of the amount of features some of these packages offer. I won't run through this entire table, but will cover a few of the technologies in more detail in the following slides. And I encourage you to read the final report when that's available if you want any more detail about a specific package. A few technologies of note that we will not be covering in detail today that I just wanted to touch on are zone balancing by 75F. So this places dampers on large RTUs to provide conditioning to only necessary areas. Digi-RTU, which varies the compressor capacity and evaporator fan using a VFD. And then Swarm Logic, this is a way to coordinate RTUs to run them in a more efficient way, which can reduce peak demand and produce energy savings as well. So the packages I will be discussing in more detail are 5 that were field tested as part of this project. So first we have the Catalyst package. So this is the most well-known package available and employs a variable frequency drive on the evaporator fan as its main source of energy savings. So this was one of the packages studied in our previous research project, and since that time has offered 3 different tiers of products. So first is the Catalyst Lite, which is simply a standalone VFD. The Catalyst itself, this is the most popular, which adds economizer controls and demand control ventilation. And then finally, the Catalyst with EIQ adds an automation system to give a live picture of the system and allows the customer to make adjustments as necessary. Turntide motors offer a full replacement of the evaporator fan motor. So typically RTUs use induction motors. So these are single speed and generally inefficient. So Turntide's product is a switched reluctance motor. This is a high efficiency motor that is inherently variable speed. Turntide's smart motor system includes the motor electronics, networking, and IoT platform capabilities. It is comprised of a motor controller, gateway, and also uses the cloud. So DrivePack offers two different packages that also employ a VFD on the evaporator fan to vary the fan speed. It's unique in that fan speeds are set at the time of installation to match requirements of the RTU during the various modes of operation. So these modes are heating, cooling, and then fan only. The standard DrivePack is a standalone VFD. The ARC, or Advanced Rooftop Controls package, adds economizer optimization, demand control, ventilation, and fault detection. The Honeywell Jade economizer provides advanced economizer controls for an RTU. So the Jade allows multiple sensor inputs, including mixed air temperature, outside air temperature, outdoor air enthalpy, and CO2. So in addition to the economizer controls, additional technologies can be incorporated in the advanced RTU retrofit solution. So this includes a variable frequency drive, demand control ventilation, a web-enabled thermostat, fault detection and diagnostics, and then building automation system integration. So the final package I'll be going into detail is the Belimo Zip Economizer. So this is an advanced economizer solution which is similar to the Jade. During installation, the installer simply enters the zip code of the RTU location, and the Zip Economizer recognizes that climate zone and will automatically set the high limit changeover temperature. The Zip package includes the economizer, air sensors, an energy module for demand control ventilation integration, and the necessary retrofit hardware needed kind of for a drop-in replacement. So it also allows for plug and play of additional sensors as needed. So controls were assessed as part of the technology assessment, but not field tested as a part of this project. So I won't go into specifics on these, but the report discusses them in a little more detail. So these systems were made specifically RTUs in commercial settings, and they can offer networking, multi-unit access, and integration with other retrofit technologies. All right, so now I'm going to pass it off to Mason to talk about the interviews that were conducted as part of this project.
Thanks, Alex, and hello, everybody. So 11 interviews were conducted with representatives from various utilities, 5 from Minnesota and 6 from national programs. These were conducted to gather information regarding their RTU and retrofit offerings. The main goal was to gain a better understanding of specific areas where they have had success or challenges with the HVAC market, and to gain insight into each utility's approach to marketing and sales, trade ally engagement, project review, and rebate logistics. According to the Minnesota utilities interviewed, most RTU-related savings in their portfolios tend to come from the installation of variable frequency drives and install or repair of economizers. The interviewees agreed that it is a challenge to achieve large amounts of savings through RTU programs. One reason cited for this is that on a per-project basis, high-efficiency RTUs do not yield large savings over baseline efficiency units. This is likely because the term high efficiency typically refers only to the cooling side for RTUs. Another challenge for achieving savings from RTU measures is the trend seen by Minnesota utilities that customers often operate their RTUs until failure before replacing. Customers are often reluctant to invest significant resources into retrofitting their existing RTUs, and more often than not, wait to install new RTUs until after the existing unit has failed. There were many reasons mentioned for this, but the most common was that building owners often lack awareness about their equipment and what's available. Utilities throughout the country were interviewed with a goal to recruit utilities from as many regions and climates as possible. Prescriptive and custom rebate programs were common in the utilities interviewed, and they also highlighted additional RTU-focused program types that they offered through their portfolios. Interviewees reported that low participation numbers motivated them to look for other avenues to engage with the RTU and RTU retrofit markets. Midstream programs were particularly common among all utilities outside Minnesota, and all utilities either offered midstream incentives or are currently looking to add them to their programs. The RTU retrofit program implemented by Bonneville Power Administration was found to be the most effective among the programs analyzed in this study. The Rooftop Unit Control Program utilizes a tiered approach, Advanced Rooftop Controls, or ARC, and ARC Lite as the two tiers. This program has specific retrofit packages that are incentivized, listed in the shown tables. The program utilizes a tiered approach and a dollar value per ton, which offers higher incentives for larger units that install equipment with more energy-saving features. For example, a 10-ton RTU retrofitted with a Catalyst Light VFD or Drive Pack Simple VFD would receive a $1,000 incentive, while the same RTU retrofitted with the Catalyst with EIQ, VFD, BAS, DCV, Advanced Economizer Control would receive $2,000 at the time of retrofit. We conducted in-depth interviews with 14 industry professionals. These contacts were made through previous and current research, as well as an in-depth market scan to determine the major market actors involved in the Minnesota supply chain for efficient RTUs and RTU retrofit. Each formal interview used a survey instrument that started with a set of base questions, followed by questions tailored to each group for further understanding of the role each group plays in the supply chain of RTUs and RTU retrofit technologies. Interviews were conducted with 5 mechanical contractors, 5 manufacturers of RTU retrofit technologies, 2 building owners/facility managers, and 2 distributors. HVAC contractors have a very strong influence on system design and operation since they directly communicate with customers purchasing HVAC equipment. Generally, RTUs are a place on failure and customers work with contractors to replace an RTU to get a unit up and running as quickly as possible. Contractors expressed concern about the cost, payback, and lack of prescriptive rebates available. There were a mix of responses when asked about high-efficiency equipment, which for RTUs is on the cooling side at the time of replacement. But some said they were likely to recommend them if the incentives offset the incremental cost from a standard efficiency unit. Overall, custom rebates were mentioned as a major barrier for retrofit technologies. Manufacturers mentioned that contractor engagement and involvement is crucial for retrofit implementation. Many manufacturers have started to reach out directly to customers, focusing on owner-occupied buildings and chain stores with national accounts. This offers them the easiest path to implementation, as decision makers can approve installations on many buildings and RTUs. Ultimately, contractor engagement and getting them on board is very important for these packages to penetrate the market. Distributors mentioned that high-efficiency RTUs are becoming more popular as a replacement option, as incentives mostly offset the incremental cost. Also, new standards require staged evaporator fans, which would not require a VFD or motor replacement as a retrofit, as these systems are already equipped to vary the speed of the fan. Building owners cited that payback period is the biggest factor when considering investing in RTU retrofits. Systems with long payback periods generally do not get implemented. Owners are unaware of available packages for retrofit. If they do not hear about them from their servicing contractor, they likely are not familiar with options for upgrades. Also, system failure and callbacks are a concern with new and unfamiliar technologies. And with that, I will pass it back to Alex.
Great, thank you, Mason. Now we will switch gears and jump into the next phase of the project, which was doing field measurements. So data was gathered from 8 field sites to determine the performance and energy savings of a variety of retrofit packages. Our goal was to choose packages we thought would have the most impact and then take short-term field measurements to gather information about each system and calculate kind of overall energy savings. The picture here shows two of the measured packages. The left shows the turn-tied switch reluctance motor package, and the right shows the Belimo zip economizer package. So there were 8 total field sites and a variety of just the number of RTUs on each building. This is common with RTUs, as some buildings only have a single unit, and we can see buildings with 40 to 50 RTUs. So there really is a wide variety in the number of units as well as the size and configuration. The RTUs field tested served multiple building types and space types, including open office, warehouse, light industrial, conference rooms, and offices. Since there was a variety of technologies and packages as part of the field study, the monitoring approach varied to match the specifics of the package. For each test site, we measured total RTU electrical energy consumption with a true power meter or RTU current that was correlated to a true power measurement to really get the most accurate information. For RTUs equipped with a retrofit that varied the speed of the evaporator fan, measurements were taken of the fan only. Some other parameters that were measured include the gas burner signal during the winter months. This was to get an idea of the operation of the system under heating conditions. Cooling call signal for the RTUs retrofitted with economizer packages. This was to determine when the thermostat was calling for cooling, so we could assess if the unit was economizing versus running the compressor. Space temperature and relative humidity to see if there were any impacts in comfort levels and if the retrofitted units were properly conditioning the space. Size plays a big role in retrofit savings potential. Larger units have larger components, so such as motors, compressors, they produce higher airflow, etc. And they have potential for higher savings. The sizes of the RTUs in this project varied from 3 to 15 tons, with an average of around 7 tons. Previous market characterization work showed that the average RTU size of an RTU in Minnesota is 10 tons. So this is slightly larger than the units studied in this project, but we felt like we found a good mix of sizes and configurations of units to characterize the performance of a wide mixture of systems. RTU sizes are always classified based on their cooling capacity, which is the tonnage of the unit, and can have varying heating input rates. Now, to properly analyze data from a variety of retrofit packages and field measurements, we used 3 main approaches for the analysis. Technologies that vary the speed of the evaporator fan, 2 analysis methods were used. The first using measured field data. So this is pre and post power measurements, along with nameplate information to create annual performance models at hourly intervals using a calculation tool for RTUs. So this tool was developed by CEE for use on our HVAC programs and creates accurate models using various inputs from the RTU and then weather data from a typical meteorological year. So using this method, a baseline model was created, then duplicated along with a VFD retrofit. This was using kind of the measured power values from the field study to compare annual energy use under both configurations. So this method was used for the RTUs retrofitted with the catalyst and turn-tied packages. The second approach was using previously measured power data and applying estimated fan speeds during different modes of operation to create a pre and post model. So that's before and after retrofit. This approach was used for RTUs that were retrofitted with the Drive Pack package. Lastly, the data for the economizer packages was collected during shoulder seasons, and this was really to characterize performance of first the standard RTU operation, and then after retrofit to capture data during expected periods of free cooling. Now the three plots here show the outputs from the various approaches. Sorry, they're a little small, but I think they kind of give you a picture of what they looked like. So the plot on the top left shows the calculator output, which creates electricity and gas regressions for a full year, and then creates a change point model to show the electric load for the RTU. This allows us to calculate annual electricity use of a standard RTU and then one with a variable speed fan. The plot on the top right shows the pre and post regressions created for the RTUs retrofitted with economizer packages. The data was analyzed to determine kind of the overall energy savings during the outside air temperature period during the field study. Finally, the change point models shown in the bottom plot. These analyzed a full year of actual RTU data and applied expected VFD fan percentages to generate savings estimates. To get an idea of how the variable speed fans operate, the plots shown here represent operation from RTUs equipped with turn-tide switch reluctance motors. So each plot shows a typical day of operation under similar weather conditions for the pre and post period for 4 RTUs in the study. So each one of these plots, I know it kind of looks like we installed the motors at midnight with the pre and the post, but really these are 2 separate days from before and after retrofit that we felt were similar enough to compare. So the blue lines represent baseline operation, which is a single speed fan that runs at 100% fan speed every time it runs. With a variable speed fan, evaporator fan speed is increased for cooling and heating operation to ensure proper airflow across the evaporator coil or the heat exchanger. And this is represented by the fluctuation in the red line. So you see in the post period on the right of each plot, that fluctuation represents the various modes of operation. And for this was during the winter, so that was heating operation. The top 2 plots, RTU 5 and 6, these are staged units. So staged in heating in that there are 2 separate stages to that fire depending on the heating capacity necessary. So these motors sense when that second stage kicks in and then ramps up the fan speed to provide more airflow across the heat exchanger. Really just what we're trying to show with these plots is just the significant power reduction that a variable speed fan can have. The plot shown here represents a typical day of operation for one of the test RTUs after an economizer package was installed. So this RTU had the highest potential for an economizer to operate in free cooling mode at this test site, as it serves exterior offices that are exposed to sunlight in the morning. On a cool morning, as the sun offers solar radiation to heat up the space, the thermostat warms and calls for cooling. And since the outside air conditions are in the threshold for economizer operation, the economizer is allowed to use the outside air to cool the building instead of turning on the compressor. The unit economizes until around 5 a.m. At that point, the compressor starts the cycle on and off until the outside air temperature is high enough that the unit stops economizing. And then from that point on, there's mostly compressor operation throughout the day. Now this is a similar situation weather-wise with a different operation. This is kind of a key finding from these advanced economizers. So the packages that have multiple advanced settings that control the operation of the RTU. So these standard economizers, or a standard economizer on just the standard RTU, generally use a simple outside air temperature sensor to judge when the system should use free cooling or just pull in outside air only for cooling. The packages studied for this project employ multiple sensors and adjustable settings to maximize the benefits of the economizer. In addition to outside air conditions, both economizer packages can measure return air temperature and mixed air temperature for more control. So for example, shown here in this plot, both of the economizer packages use a setting that can economize when the outside air temperature is above the switchover temperature if it's below the return air temperature. So it can really just look at the return air temperature and say, outside air temperature is lower than this, we can use this for cooling. So there's a dead band setting that the installer can adjust. So it's just a number that the outside air temperature is from the return air temperature. In the test units that were studied, specific RTUs showed economizer operation when the unit called for cooling and the outside air temperature was above the switchover temperature of 60 to 65 degrees, as shown in this plot. So as you can see, the RTU maintains a cooling call from 2 a.m. to around 10 p.m. with fan-only operation, because the economizer controller determined that the outside air would be adequate to cool the space and did not turn the compressor on. Now, a key finding to the field study of economizer packages was the reduction in compressor runtime. The plot here shows the decrease in compressor runtime between the pre and post test periods. So each bar represents the percentage of time that the compressor ran while the RTU called for cooling. The blue bars represent the pre-period or before retrofit, and the orange bars represent the test period after retrofit. So if the compressor was not running during the cooling call, the unit was economizing. During this time, the outdoor air damper was open and the evaporator fan pulled in outside air to cool the space. 3 technologies were tested that vary the speed of the evaporator fan as their main source of energy savings. These were the catalyst VFD, the turn-tide switch reluctance motor, and the drive pack VFD. RTUs equipped with the catalyst package saved an average of 36% of annual electricity consumption. This is around 2,700 kilowatt hours per year. Turn-tide switch reluctance motors saved an average of around 33%, or 35 to 3,600 kilowatt hours per year. And the drive pack saved 43%, or 3,600 kilowatt hours per year. These values represent the average savings across all RTUs in the study for each individual technology. So you'll see the final 2 rows in this table. Energy savings from RTUs retrofitted with economizer packages ultimately did not meet expectations and resulted in long payback period, while some RTUs demonstrated a moderate energy savings of around 2 to 9%, 3 RTUs experienced negative savings. So optimal scenarios for achieving energy savings when retrofitting an RTU with an advanced economizer package in Minnesota include focusing on larger RTUs, building types that have high internal heat gain. So this can be from people, equipment, lighting, such as industrial, manufacturing settings, or conference rooms that are frequently used. And then a colder climate such as Duluth or northern Minnesota that really can provide a higher fraction of ideal outside conditions for free cooling. So as expected, annual electricity savings increased with RTU size. So the plot shown here is focusing on the RTUs that were specifically retrofitted with variable speed, something that can vary the speed of the evaporator fan. So smaller size RTUs are common on Minnesota buildings. And while savings potential is somewhat limited on these units, they can really still offer reasonable payback periods if runtime hours are significant. So a key factor for savings is runtime hours, also how an RTU is operated, and then how they interact with other RTUs in the building. Payback period is an important factor when customers are considering efficiency upgrades, and generally projects are not considered if a payback period is higher than 5 years. Ideally, this payback period is in the 2 to 3 year range. Payback periods for the 3 packages that vary the speed of the evaporator fan are shown in this plot based on our analysis. You can see that they fall within the 2.5 to 7 year range. Just as a note, these payback periods represented on this plot do not incorporate any incentives and are strictly based on energy savings in the initial cost of the system. So to give you just an idea of the impact of an incentive from a Minnesota utility, so by using a $400 rebate, which is an average based on kind of the motor sizes in this study, payback periods shown in this chart generally decrease by about 1 to 2 years and put most of them under that 5 year and under payback period. So assessment of the overall market of retrofit options and results of the energy savings calculations were used to create decision support tools. These were done to help determine which options are most suitable for particular use cases in Minnesota. So the created tools are intended for building owners, contractors, SIP program administrators, and utility staff to summarize the findings from the study and inform decisions related to retrofitting packaged RTUs. So the decision tree shown here was part of the tool that will be given to contractors to use when assessing an existing RTU to look for retrofit opportunities. So this tool asks a series of questions to guide a contractor through that process and either end up with a potential retrofit that they can explore or if no action is needed on that particular unit. Okay, so just wrapping up with a summary of the market barriers that were found during this project. A big hurdle in the market is that RTUs are replaced only when they fail. And when they do, building owners and contractors make quick decisions to get a working RTU to condition their building. This often leads to standard efficiency equipment and rarely retrofit opportunities on existing RTUs. Custom rebates are generally burdensome and complicated. This can steer contractors and building owners away from implementing efficiency upgrades that require them. RTU runtime and savings can be highly variable, as shown in previous research as well as the study. Engaging contractors to represent and recommend products has been difficult for the manufacturers of retrofit technologies. Leased buildings offer another challenge where building owners might not want to invest in efficiency upgrades. So in these situations, those who lease the building can be responsible for the energy bills and building owners responsible for purchasing the equipment. So, these situations can make the purchase of efficiency upgrades complicated. And then this contrasts with owner-occupied buildings where the owners pay for both. And then new standards have introduced similar technologies incorporated on newer RTUs. So this can be a stage evaporator fan and more robust economizer control. Finally, wrapping up with some recommendations from the study. Contractor engagement is crucial for market adoption of these packages. So by proving energy savings, reliability, and payback periods with research like this project, as well as other third-party verification, contractors can get on board with representing these products. Customer engagement is also important to get customers interested in the products. So reaching out with direct communication, newsletters, etc., can help initiate conversations with utilities, contractors, and manufacturers to really start that process to determine if there's an ideal retrofit opportunity, and then work to find approved installers to implement them. The number one recommendation through all of the interviews as part of this project was to include as many prescriptive rebates as possible. Adding prescriptive rebates as well as simplifying the custom rebate process as much as possible can increase adoption. Using a tiered approach that outlines specific products and gives a dollar per ton incentive can really help get the word out on specific packages and then offer customers a specific dollar amount based on the size of the unit. And then finally, continuing to modify TRM measures is a way to more accurately predict savings. Thank you, everyone.
Thank you, Alex and Mason, for your great presentation. Attendees, if you have not already done so, please go ahead and type any additional questions into the Q&A panel to send them our way as we transition into our Q&A time for today. So our first question today is, can you clarify what a VFD is?
Sure. VFD means variable frequency drive. Really, this is a piece of equipment that is placed on an existing motor. So for the one studied in this project, that was on the supply fan, or the fan moving air throughout the system. And the goal of the VFD is really to just slow down or decrease the speed of that fan so that you don't need to provide 100% airflow during operation.
Great. Let's see, next question. How were cooling calls measured?
So cooling calls were measured. We've used this in previous research. It is a device that hooks up to the terminals on the RTU itself. So this is on the terminals where the thermostat wires land. So we can tell, when the thermostat calls for cooling, it produces a signal. We steal that signal and then output a pulse measurement based on just runtime of that, and then have a separate logger that kind of just measures. It just creates a count and just measures the total runtime of the cooling call. So a pretty unique device that we had made for a previous project.
Excellent. Our next question is, are heat pump RTUs viable in Minnesota, and who makes them?
Yeah, that's a good question. So CEE does quite a bit of research on heat pumps, and we are starting to look into heat pump RTUs more. We will be kind of starting some field demonstrations of those systems. They are becoming more viable as they kind of incorporate the variable capacity compressors into those systems. So we know of ones by Trane and Daikin are probably the most notable right now, but we certainly expect others to kind of join that.
Continuing to move on as we are getting questions in, this is great. Does the passage of the Inflation Reduction Act have any effect on the process of these retrofits?
Yeah, that's a good question. I'd have to do a little bit more research into that. Obviously, I know those affect heat pumps, so heat pump RTUs that we just talked about, but um, not exactly sure on the specific retrofits. I'd have to do some more research into that and get back to you. So certainly happy to chat after the presentation about that.
The next question is, how can we obtain an electronic copy of slides and the report? And I can take that one. I'll also spend a couple of minutes too after we close Q&A to go through this again. But the slides and the webinar recording and the final report will be available on the department's website, and I will show you that before we close today in the coming weeks. And if you need the slide deck or would like the slide deck before that time, feel free to email me directly, Lindsay, and I will give you, which I will give you my email address here soon, so I could send that to you earlier as well. Okay, next question. Thank you. Can you provide specification for the sensors? No disruption with those signals seen in the field. And I believe this is related to the cooling question that was earlier.
Yes, that sounds right. Yeah, I'm happy to kind of touch base afterwards and give you the specs on those. No major disruptions with those. They seem to work pretty well for us, and it's a pretty unique and nice way to measure a call from a thermostat.
Okay. Is the device for measuring call for cooling commercially available?
No, well, there may be something available, but that was designed specifically for a previous project that we use.
Okay. The next question, who to contact to be a demo host for a heat pump RTU?
You can reach out to me afterwards and I can kind of facilitate that. We're always looking for buildings for future research, so I'm happy to kind of to field that afterwards.
Okay. I'm going to ask one or two more questions and then move on to closing out. So the last question, or second to last question, can you dive more deeply into why the energy savings related to the economizers were less than expected?
Yeah, absolutely. That's a good question. There are challenges of monitoring in commercial spaces. So RTUs can have interesting interactions with one another, and small set point changes to kind of specific units can have a significant impact on how much a unit runs. So many of the units for this particular field site really did not show significant cooling runtime. So this is something we found in the project as well as past research that RTUs that serve the same space type, which for this field site was an office space, a large open space, operate differently based on kind of the thermostat set points. Because of this, some of the units just simply won't run a lot, and then others will run more. So for units that rarely run, a few cooling events in kind of that pre-period can have a large impact on the calculations and results. There wasn't a lot of internal heat gain from equipment, people in this particular field site, which can have a big impact on the amount of cooling operation of RTUs. And then also, shoulder seasons in the test period for this showed kind of limited free cooling opportunities. So in recent years here, we've kind of seen this trend where we seem to jump right from summer into winter, or vice versa, and kind of offer some limited opportunities for economizing. But overall savings were lower than expected, but I don't really think it's indicative of the packages not working correctly. And then savings are expected to be much higher in a more ideal application.
All right, thank you so much. So attendees, if you have any additional follow-up questions about this card project after the webinar, please feel free to contact Alex or Mason directly, and their email addresses are on this slide. The recording of this webinar and slide set will be available on the department's website, along with the final report in a couple of weeks to a month. When available, currently, you can link to either of these from the quick links on our Applied Research and Development webpage as indicated on this slide. The department's R&D webpage has additional resources and information related to the CARD program and to CARD research projects, which you can check out by going to the address here. The department's website recently underwent a major change and is continuing to undergo some improvements. So please do not hesitate to contact me directly. Lindsay Anderson, my email address will be on the next slide. If you have any questions or concerns related to accessing CARD research, posted here, or like I said, the slides from today. There will be a short evaluation that launches after this webinar. Please take a few minutes to fill it out and let us know how we did. And finally, thank you all for participating today. We appreciate your interest in CARD projects. Before I let you go, I want to take a minute to mention one upcoming CARD webinar. On July 20th, other staff from Center for Energy and Environment will join us to discuss results from a different CARD project titled, How Smart Do Intelligent Buildings Need to Be? So to keep abreast of upcoming CARD webinars as they are scheduled and other news related to the Minnesota Conservation Improvement Program, you can sign up for SIP updates through our email list, which is there's information on our website, or you could use this link, or feel free to contact me to be added. In the meantime, feel free to contact me with questions or suggestions for CARD or CARD webinars. That concludes the webinar today. Have a great day. Bye-bye.